Welcome to Math 201, lesson 3.5, trig derivatives. I'm going to give you a little bit of a warning before I get started here that this lesson presupposes some trigonometry prerequisite knowledge. If you find that you are not following parts of this lesson because you have some gaps in your trigonometry knowledge, I am going to post a trig review video that you could go back and watch before watching this video. Okay, so I'm going to tell you this interesting fact. One of the functions, sine or cosine, is the derivative of the other. We're going to try to figure out which one is which and explain how we know. Let's start by sketching the graphs of sine and cosine. These are graphs that you should know the shape of and know how to draw a quick sketch of them without looking something up. Okay, so I'm going to start with y equals sine of x. I know that the sine starts at its midline and it hits its midline halfway through and again at the end of its period, which is 2 pi, and it hits a max in between 0 and pi and a min between pi and 2 pi. And then I can connect these with a nice smooth curve. Okay, and then I'm going to graph y equals cosine x on the next set of axes, and cosine starts at its max and ends at its max, hits a min halfway between, and then zeros halfway between the maxes and mins. And so my graph, when I do a nice smooth curve, looks like this. All right, using those graphs that we just created, I want to fill in these charts about when each of these functions, sine and cosine, is increasing, when is it decreasing, where is it positive, where is it negative. Because I know there's a relationship between a function is increasing and its derivative is positive. And when a function is decreasing, its derivative is negative. So I want to see if I can see this relationship between sine and cosine or cosine and sine. Okay, so let's just look at sine, which is this graph on the left here. Where is the sine function increasing? That would be from 0 to here, which is pi over 2. Okay, and then it's decreasing from pi over 2 to 3 pi over 2, but it's increasing from 3 pi over 2 to 2 pi. So it's increasing again from 3 pi over 2 to 2 pi. And it is decreasing between pi over 2 and 3 pi over 2. Continuing to look at the sine function, let's analyze where is it positive and where is it negative. So positive meaning where is it above the x-axis and negative where is it below the x-axis. So the sine function appears to be above the x-axis between 0 and pi. So we say that function is positive between 0 and pi. Okay, and then where is it negative? That's between pi and 2 pi. The graph lives below the x-axis, so the y values are negative. We say that means that the function is negative between pi and 2 pi. Okay, let's do a similar analysis for cosine. Where is it increasing? Where is it decreasing? So we're increasing from here to here, so from pi to 2 pi, and decreasing from 0 to pi. And where are we positive? Where are we negative? So we're negative here to here, right? This little chunk is below the x-axis, pi over 2 to 3 pi over 2. So there's my negative portion. And then I'm positive from 0 to pi over 2 and from 3 pi over 2 to 2 pi. So positive from 0 to pi over 2. And again from 3 pi over 2 to 2 pi. So let's look at, I see some overlap here, like sine um, when sine is decreasing from pi over 2 to 3 pi over 2, cosine is negative there. And we know that that is a relationship between a function and its derivative. When a function is decreasing, the derivative is negative. Okay, and when the sine is increasing on the interval 0 to 2 pi and 3 pi over 2 to 2 pi, what is cosine doing in terms of its sign? It is positive. Okay, so when the sine is increasing, cosine is positive, and when the sine is decreasing, cosine is negative. That means that cosine would be the derivative of sine. So the derivative of sine has to be cosine. Let's write out our formal conclusion. The derivative of the sine of x is the cosine of x, which means we have a chain rule version of this rule. The derivative of the sine of some stuff would be the cosine of the stuff times the derivative of the stuff. Okay, so we know that the derivative of sine is cosine. We figured that out already. Let's think about the function whose derivative we don't yet know, the cosine function. I want to know what its derivative is. So I've graphed the cosine function here. I want to sketch the graph of its derivative on the same set of axes and see if we can use that to guess a formula for the derivative. So remember, we did this back in chapter 2, sketching derivatives. And the best way I think to start is to look for places where the derivative is 0. And remember, the derivative is the slope of the tangent line. So I'm going to look for horizontal tangent lines along the graph of cosine. And everywhere I see a horizontal tangent line, that means the derivative is 0. So at each of these horizontal tangent lines, I'm plotting an x-intercept or a 0 for the derivative. Okay, and then in between those zeros, I'm going to look at the tangent lines of my curve, and I'm just going to estimate their size. So after this is 0, the slope is now negative, um, and negative, and it hits sort of maximum negativeness here at about 1.5. And the slope of that looks like it is 1, okay, -1. So here at about 1.5, the slope is going to be about -1. Okay, and then here at a little after 3, which is pi, it comes back up to 0. All right, and then after this 0, if I draw some tangent lines, I have a positive slope, more positive, and then I hit sort of maximum positive slope right here, and that slope looks like it's about 1. Rise over run looks like about 1. Okay, so here at about a little after 4.5, I think that the slope is about 1. So I'm going to plot a y value of 1 there. And then I'm going to connect the curves, the points that I have so far, with a nice smooth curve. So I've got something like this. And does that look like a function that I am familiar with? Okay. So I'm just going to highlight that so that it's really clear which one we're looking at. This function is the derivative of cosine. So I've just sketched a picture of the derivative of cosine. And does that look like a familiar function? So it's not cosine and it's not negative cosine because cosine starts at 1 and goes to its midline, to its min, to its midline, back up to its max, right? It's not cosine. It's not the negative of cosine because if I flipped cosine over the x-axis, it would start at -1 and then it would go midline, max, midline, min. Um, it's not sine because sine does have zeros at 0, pi, and 2 pi, but it goes up and then down. So this is the reverse of that. This is the graph of the sine, but flipped over the x-axis. So it looks like, according to my picture, that the derivative of cosine is the sine function, but flipped over the x-axis, so we put a negative in front of it. Okay, we'll write down our official conclusion. The derivative of cosine is negative sine. And that means that the derivative of the cosine of some stuff is negative sine of the stuff times the derivative of the stuff. Okay, we're going to use this newfound knowledge we have. We know the derivative of sine and we know the derivative of cosine. I'm going to use those to try to find the derivative of tangent. So I want to find the derivative of the tangent function. And tangent is just sine over cosine. So that is a little bit of prereq knowledge from pre-calculus, that the tangent function is sine of x over cosine of x. And that means I can use the quotient rule. Okay, so my numerator is my f, my denominator is my g, and I'm going to apply the quotient rule. So this is going to be f prime g. So the derivative of the numerator, derivative of sine is cosine. Actually, I'm going to write it out. So it's going to be f prime. This is the sine of x prime, meaning take the derivative. F prime times g minus f times g prime all over g squared. Okay, and now I'm just going to take these two derivatives, the derivative of sine and the derivative of cosine. So let's see what that comes out to. This is going to be cosine x. Derivative of sine is cosine. So I have cosine times cosine minus sine x times the derivative of cosine, which is negative sine, all over cosine squared x. Okay, so I have cosine times cosine, that's cosine squared. And then I have minus sine x times negative sine x. So that's minus a negative, so that's plus sine squared x all over cosine squared x. And I'm almost out of room, but I think I can draw my conclusion. Okay, cosine squared plus sine squared, that's the most famous trig identity that exists. So if there's one, if you're only going to ever remember one trig identity, it should be this one, the Pythagorean identity. It's that cosine squared plus sine squared is 1. So this is 1 over cosine squared. And then the reciprocal identities, 1 over cosine is the secant. So this is the secant squared of x. So the derivative of tangent is secant squared. Okay, we've reached the activity for this lesson. You should pause the video, try these problems on your own, and then come back and watch the rest of this video when you are ready to see the solutions. Okay, let's go through these together. So I want to find the derivative of cotangent x. So it's important to be able to do this. I have to be able to rewrite cotangent in terms of some trig functions that I do know the derivative of. Um, and so I'm going to rewrite cotangent as cosine over sine. And then I'm going to do the same technique I just did for tangent. So I'm going to use the quotient rule to find f prime of x. Okay, so it's going to be f prime g. So derivative of the numerator would be negative sine times the denominator sine. So it's f prime g minus f cosine of x times g prime. So the derivative of sine is cosine all over the denominator squared. Okay, so this says negative sine squared minus cosine squared all over sine squared. Let's factor out a -1 from that numerator. So I have -1 times sine squared x plus cosine squared x. That's why I factored out the -1, because I wanted to use that Pythagorean identity again, just like I did in the tangent example. Okay, and then sine squared plus cosine squared is 1. So this is -1 over sine squared x. And one of my reciprocal identities is that 1 over sine is the cosecant. So this is negative cosecant squared x. Okay, for part B, I want to find the derivative of secant x. So I'm going to use my reciprocal identity that says this is the same thing as 1 over cosine x. And I could do the quotient rule on 1 over cosine x, or I could rewrite 1 over cosine as cosine to the negative 1, and use the chain rule. So this is what I'm going to do for this one. I'm going to do the chain rule. I'm going to take the derivative of cosine x to the negative 1. So my inside function is cosine. So my outside function is the negative 1 power. So this is going to be some stuff to the negative 1 power. And I'm going to start with the power rule. Bring the negative 1 down, copy the stuff, reduce the exponent by 1, then multiply by the derivative of the stuff. Okay, so that's negative cosine x to the negative 2 times the derivative of cosine, which is negative sine. And I have negative times a negative, they cancel, and I get sine x over cosine squared x. So my negative and my negative multiply together to make a positive. And I'm taking this factor that has a negative exponent, moving it to the denominator and making the exponent positive. And I could leave it like this, but I could simplify it also. So I could rewrite this as sine over cosine times 1 over cosine, because sine over cosine is tangent and 1 over cosine is secant. And I could have stopped at any point. I could have said this was the derivative. I could have said this was the derivative. This is just a convention that when somebody asks you, like, what is the derivative of secant x, you say it's tangent x secant x. Okay. This is just the most common way that the derivative is written. Okay, this one is very similar. I'm going to take the derivative of cosecant x. And again, I'm using my reciprocal identity that this is 1 over sine. And this time I'm going to try using the quotient rule. I just want to use the quotient rule this time for practice. I could write this as sine x to the negative 1 and do the chain rule like I did on the previous example. But instead, this time I'm going to call my numerator f and my denominator g and do the quotient rule. So my derivative of 1 over sine is going to be f prime. So that's the derivative of my numerator. The derivative of 1 is 0. F prime times g minus f times g prime, that's the derivative of the denominator, which is cosine x, all over the denominator squared. So that whole term just goes away because 0 times anything is 0. So this becomes negative cosine x over sine squared x. We could call that the derivative, but it is convention to simplify this a little bit. And in the same fashion that we did in the last example, I'm going to rewrite this as negative cosine x over sine x times 1 over sine x. And cosine over sine is cotangent. So this is negative cotangent x, and 1 over sine is cosecant. So this is negative cotangent x times cosecant x. Number 2, calculate derivatives of each of the given functions. Are there any identities that you can use to make this easier? Okay, so cosine squared plus sine squared, we have discussed a couple of times in this lesson that sine squared plus cosine squared is always 1. This is called the Pythagorean identity. It's the most famous trig identity there is. So if I want to take the derivative of cosine squared x plus sine squared x, I'm really just asking you to take the derivative of 1. And the derivative of any constant is 0. Let's just do it using the chain rule just to make sure that it comes out the same. So I'm going to take d dx of cosine of x squared plus sine of x squared. Notice I, instead of using the conventional notation of putting the squared between the function name and the variable, I did the more traditional way of say putting parentheses around the cosine x and then squaring it. These mean the same thing. I like it written this way to remind me that this is some stuff squared plus some stuff squared. So when I take the derivative, I'm going to do the power rule. So this is going to be 2 cosine x to the first, and then times the derivative of the stuff, which is negative sine x. And then I have plus, I'm going to use the power rule on sine x squared. So that's going to be 2 sine x to the first, and then times the derivative of the stuff, and the derivative of sine is cosine. So this does come out to negative 2 sine x cosine x plus 2 sine x cosine x, and those two terms add up to 0. For B, I have secant squared minus tangent squared. This is another version of the Pythagorean identity. So I'm just going to write a little aside over here. If we start with the famous Pythagorean identity that sine squared plus cosine squared equals 1, and I divide both sides of this equation by cosine squared, sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. So this is another version of the Pythagorean identity. Tangent squared plus 1 is secant squared. And if I subtract tan squared from both sides, I get 1 equals secant squared minus tan squared. And that's what I'm trying to take the derivative of. So taking the derivative of this is the same as taking the derivative of 1, which is 0. And you've probably got the hint by now that this is going to be another Pythagorean identity. So I'm going to start again with sine squared plus cosine squared is 1. And this time, instead of dividing both sides by cosine squared, I'm going to divide by sine squared. Okay, so sine squared over sine squared is 1. And cosine squared over sine squared is cotangent squared. Oops, it's supposed to be 1 plus cotangent squared equals 1 over sine squared is cosecant squared. So if I subtract cotangent squared from both sides of this equation, I get cosecant squared minus cotangent squared, which is 1. So really, I'm just trying to find the derivative of 1 again, which is 0.